Hello everyone. In this video we're going to be discussing section 10.8, compare linear, exponential, and quadratic models. Alright, so in previous chapters we've talked about linear functions, we've talked about lines. We did talk about exponential functions a little bit. That's really what you're experiencing right now if you're watching the news at all, because of this pandemic and all the diagnoses of the coronavirus. So as soon as one person's infected, then 2 people are infected, then 4, then 8, then 16, 32, and it just climbs exponentially. Alright, and then there's also quadratic models. So let's go ahead and start by just looking at their general graphs. So a linear function is written as y equals mx plus b, and it's anything that can be written in that form, and it's going to look like a line, whether it has a negative slope like this or whether it has a positive slope. It is a linear function. Alright, an exponential function, it starts off really steady and then shoots up into space. Or you also have, so this is called exponential growth. This is an example of exponential growth. Or we have what is called exponential decay, which is something like radioactive isotopes. Alright, so it starts off with a very sharp decline and then it really trickles off. So it looks something like that. Alright, it's the mirror image of the exponential growth. And then our quadratic function is what we've been working on in this entire chapter, and that is modeled by a beautiful parabola, and its standard form is y equals ax squared plus bx plus c. So let's go ahead and look at example 1 and see if we can determine what type of function is represented. Alright, so we have these lovely ordered pairs. So we're going to go ahead and need to graph them. Now, it's going to be pretty tricky to graph 1/32 and 1/8, but then from there, it should be easy to graph those points. So when I graph them, I get this beautiful shape, and I can easily tell that that is an exponential function. Alright, when I graph these points, these sets of points, I see that they fall into a beautiful line. Of course, you want to connect the dots and see if you can predict the trend that's happening. And here, with these sets of points, I end up with a quadratic function. Alright, so if I give you a set of points to graph, you need to be able to kind of connect the dots, see where it's coming from and where it's going, and what sort of function is going to best represent it. Alright, so here is a whole bunch of information. This is all in your textbook. If I give you points like that and you are not able to graph it, we have a couple things that we can try out and look at. So I'm going to start reading this to you. A table of values represents a linear function if the differences in successive y values are all equal. So what they do is they took 5 minus 2, and then they took 8 minus 5, and then they took 11 minus 8. And they found that all of those differences were equal and were 3. So that represents a linear function. Alright, so a table of values represents an exponential function if the ratios of successive y values are all equal. Now this is a little bit different. We are not subtracting, we are dividing. So they take 0.5 divided by 0.25 and 1 divided by 0.5 and 2 divided by 1. And they come out to 2 every single time. So that is an exponential function. And then for a quadratic function, you actually have to do the differences twice. So let's go ahead and say you tried it out, you were thinking it was linear, but then you got these differences. Well, you know from there that it's not going to be linear because they're not all the same. So you try out the differences again, and they come out the same, which means it is a quadratic function. One hidden direction that they kind of squeak in there with this side note that I pulled up for you guys is This is only true. This is only true if the x values are increasing by the same amount. All right, so if I look at all of these x values in the table, they are all increasing by 1 every single time, left to right. All right, so it's really easy to kind of skip over that. So you're going to want to go ahead and the very first thing that you do is check your x values and see if they're if the points that they're giving you are increasing by a constant amount. It doesn't have to be by 1. It could be by 5s or 2s, or I don't know, maybe you're a little bit funky and you like to increase it by 67 every time. So as long as it's consistent from x value to x value, then we can apply these rules. All right, so let's look at another example. So we're going to use these differences or ratios. So I'm going to go ahead and look at my x values first. Make sure that I'm increasing by 1, increasing by 1, increasing by 1. Okay, I'm good. So I can go ahead and use these ideas here. So from -6 to -6, that is a 0. And then -6 or -4 minus -6, that's a 2, 4, 6. All right, so the first set of differences means that it's not linear. Those numbers are not the same. So I try it again, and I find out that the second set of differences are all equal to 2. So that means this is a quadratic function. Our next example, 2b here, I double check all of my x values. I am increasing by 1, so I can go ahead and go along with this. All right. So I look at what's happening, and I do a set of differences, and they all actually happen to be the same. So 1 minus -2, 4 minus 1, 7 minus 4, 10 minus 7, all end up with a difference of 3. So that means this table represents a linear function. Now, you could try these differences and fail both in the first round and the second round, but we'll get to that. All right, so guided practice, here are some points. You can graph it, that's one option, or you can put them in a table and see if you can set up the differences or ratios. All right, so writing an equation. When you decide that a set of ordered pairs represents a linear, exponential, or quadratic function, you can write an equation for the function using the information that they're giving you. So, in this lesson, when you write an equation for a quadratic function, the equation will have the form y equals ax squared. All right, so if it's quadratic, we definitely need that x squared piece in there. That is what makes it quadratic. So here is example 3 for you. Tell whether the table of values represents a linear function, exponential function, or quadratic function. Then write the equation. All right, so step 1, double check your x values. They are increasing by a constant amount of 1, so we are golden there. So then I want to go ahead and determine what type of function I have. So I can find the first set of differences, and they are not the same, so it's not linear, so go ahead and cross off linear. The second set of differences lands me with a common difference there of 1. So that means this is quadratic. So the table of values represents a quadratic function because all the second differences are equal. So step 2, write an equation for the quadratic function. We're going to be using this y equals ax squared, and then we find the value of a. We find the value of a by using the coordinates of a point that lie on the graph. So you could use any of the points that they have, any x comma y, as long as the point is a coordinate pair that has the proper x and y together. Okay, so you're going to substitute in x for x and y for y. So this is what it looks like after one step. And you might be questioning, why did they pick this point? Well, because x equals 1. That's really easy to deal with. So then they can solve for a really easily. So a equals 1/2. So the answer, then our final answer for the equation is y equals 0.5 x squared. All right, and then you can plot the ordered pairs, and then you can also overlay the graph using a graphing calculator, and you would see that all those points are on that graph. All right, and you don't need a graphing calculator to do that. You can do that at desmos.com. So here's another guided practice for you. See if you can find what type of function it is, and if you can write an equation. All right, example 4. The table shows the breathing rates y in liters of air per minute of a cyclist traveling at different speeds in miles per hour. All right, so yada yada, word problem, no big deal. We're still doing exactly what we have been doing. So we've got 1, 2, 3, 4, 5, 6 different points here, and we need to determine a relationship. So we graph it, and you know, it looks straight, but it also looks maybe a little bit curved. I'm not quite sure here. So I graph the data. It has a slight curve. You can see if it was really exaggerated like that, but maybe if you put a straight line next to it, you would see that it is not quite straight. So I don't think it's linear because it's not perfectly straight. So decide whether the model is one of the other ones. So I go ahead and take all of my y values and I divide them, and I actually get a common ratio of 1.11. So that means that all of the ratios are equal, so it is in fact exponential. It's just one really small part of my exponential graph here. So we're kind of drawing that in there, common ratio of 1.11, and it is an exponential. So into my equation, I need to use a point, so they pick 20, 51.4, and then my b value is 1.11. All right, so it kind of changes what they're talking about as far as all the variables are concerned. So when we were talking about quadratics, the value we were finding was a. Here, we still need to find a, so I substitute in that common ratio for b, 1.11, and 20 in for x, and 51.4 in for y. All right, so when I compute 1.11 to the 20th, it's going to give me some sort of crazy decimal, but regardless, in order to solve for a, I need to divide it on the other side. And I end up with about approximately 6.38. So here is my final equation, substituting in my a value for a and my b value, my common ratio, in for b. And here is your last guided practice. In example 4, suppose the cyclist is traveling at 15 miles per hour instead. Find the breathing rate of the cyclist at this speed. Alright, if you guys have any questions, please feel free to hit me up via email or take advantage of my office hours. I look forward to hearing from you guys.